Good day, students. Today, let us look into the crystal planes in the material and how to represent the planes using Miller indices. Now, the crystal lattice is regarded as a collection of an aggregate of lattice planes. We can assume the lattice to contain a set of parallel planes as such, or it can be a set of parallel planes as such, or in any other direction. So in a gist, the lattice is a collection of a lot of lattice planes containing the atoms. Now the Miller index is a shorthand notation used to describe the crystallographic directions and planes in a crystal. The number of indices will match the dimension of the crystal. That is, for a one-dimensional crystal, there will only be one index. In a two-dimensional crystal, there will be two indices, and in a three-dimensional crystal, we use three indices. So physically, we will be using three Miller indices here. The Miller indices are H, K, and L. These Miller indices in curved brackets represent a point in the crystal lattice. Note that there are commas in between these Miller indices. Now, in the square brackets, if we represent the Miller indices, it represents a crystallographic direction of that plane. The bracket notation of HKL represents a family of crystallographic directions. Again, here the curved brackets including HKL without the commas represent a crystallographic plane. And the curled brackets including HKL values represents a family of the crystallographic planes. Now let us see what we mean by the Miller index and how do we attain it. Miller index is the reciprocal of the intercepts made by the plane on the crystallographic axis when reduced to smallest numbers. So this sentence includes all the things that we do to attain the Miller index. To find the Miller index, we have to choose a lattice point and form the coordinate axis with this lattice point as the origin in the direction of basis vectors. So to start with, we have to find a point. Okay, so let this point be here, and that point is assumed as the origin, and from that origin we draw the different axes. In this figure, we have this axis to be the x coordinate axis, this axis to be the y coordinate axis, and this axis to be the z coordinate axis. Now we see the plane in it and we have to find the intercepts of that plane on the axis. So on the x axis we have the plane x intercepting here. On the y-axis, we have the plane y intercepting here. And on the z-axis, we have the plane z intercepting here. Now, we take the reciprocals of the intercepts and reduce the reciprocals to the smallest set of integers. The three integers we get are the h, k, and l values. And the Miller index of the plane is written as curl brackets HKL. In cubic crystals, the plane HKL will be perpendicular to the direction HKL. So if HKL is placed in curved braces, it represents the plane. And if HKL is placed within the square brackets, it represents the direction. And here, the direction will be perpendicular to the plane in cubic crystals. Let us see that. Here, we will see how to represent the Miller indices for lattice points. For that, let us assume a Cartesian coordinate system, x, y, z system, and place a cube with one of its edges at the origin. We are giving different names for each of the corners. O represents the origin, and all other corners we have A, B, C, D, E, F, and G. The lattice points, different points, can be written as O will be 0, 0, 0 separated by commas. A will be 0, 1, 0 separated by commas. Here we assume that this unit cell, cubic unit cell, has a unit lattice constant. So the distance OA is 1, OC is 1, OG is 1. Hence, A is represented as 0, 1, 0, B is 1, 1, 0, C is 1, 0, 0, D is 1, 0, 1, E is 1, 1, 1, F is 0, 1, 1, and G is 0, 0, 1. So in these lattice points, we can see that if the coordinate is 0, so that point is not crossing that particular axis. It does not have an intercept on that x-axis. So for G0, 0, 1, the point G has 0 intercept on x-axis, 0 intercept on y-axis, and unit intercept on the z-axis. Now let us represent the lattice directions using Miller indices. The lattice direction OA can be represented as 0, 1, 0 in square brackets, and please note the direction of this vector. OB will be 1, 1, 0 in square brackets. OC will be 1, 0, 0 in square brackets. OD will be 1, 0, 1 in square brackets. OE will be 1, 1, 1 in square brackets. Here, please note that all these orientations are emerging from the origin. OF will be 0, 1, 1 in square brackets. OG will be 0, 0, 1 in square brackets. GD will be 1, 0, 0 in square brackets. Here, to find that, we can make use of GD as OD minus OG, and from that we get square brackets 1, 0, 0. Now to find the orientation or crystal direction DG, we should make use of OG minus OD. So from that we get minus 1, 0, 0. And here for Miller indices, minus 1 is represented as 1 bar. The negative numbers are represented using bars. So here the Miller index is 1 bar 0, 0 in square brackets. Now to find the Miller index of a plane or the direction towards any negative axis, let us assume another plane HIJK behind the previous one. So in this one, OH orientation is obtained as 1 bar 1, 0 in square brackets. This is because the x-intercept here, or the x value of h, will be minus 1. Hence, the Miller index will be 1 bar along the x-axis. Now let us see how we find the Miller indices for lattice planes. Now in this unit cell shown, we have the plane ABEF. To find the Miller intercept of this particular plane, first we have to find its intercepts on the coordinate axis. So the intercepts are infinity on the x-axis, 1b on the y-axis, and infinity at the z-axis. So I write infinity a on the x-axis, 1b on the y-axis, and infinity c on the z-axis. The coordinates will be infinity, 1, infinity. Taking the reciprocals, we have 0, 1, 0, and hence the Miller index is written as curved brackets 0, 1, 0. So the Miller index of this particular plane ABEF is 0, 1, 0. Now let's look at another plane and find its Miller index. So we are taking this plane BCDE, and to find its Miller index, first let us find its intercepts on the coordinate axis. The intercepts are 1a, since it cuts the x-axis, then infinity b, since it does not have any intercept on the y-axis, and infinity c, because it does not have any intercept on the z-axis. Now the coordinates will be 1, infinity, infinity by removing the basis vectors a, b, c. And the reciprocal here will be 1, 0, 0. And hence Miller index is written by curved brackets 1, 0, 0. So the Miller index of this plane is 1, 0, 0 in curved brackets. Now let us try to find the Miller index for this particular plane OAFG. Now please note that the origin here is C. Hence, the intercepts of this plane can be written as minus 1a, infinity b, infinity c. The coordinates will be minus 1, infinity, infinity. Taking the reciprocals, we get minus 1, 0, 0. Hence, the Miller index is written as 1 bar 0, 0 in curved brackets. Now let us find the Miller index for this particular plane EFGB. First, the intercepts are infinity A, infinity B, and 1C, right? So the coordinates will be infinity, infinity, 1. The reciprocal will be 0, 0, 1, and hence the Miller index will be 0, 0, 1 in curved brackets. Now let us find the Miller index for this plane OCDG. Again, note that the origin here is shifted to A. Hence, the intercepts can be written at infinity A, minus 1B, and infinity C. The coordinates are at infinity, minus 1, infinity. The reciprocal will give 0, minus 1, 0, and hence Miller indices is written as 0, 1 bar 0 in curved brackets. Now let us find the Miller index for a bit more difficult lattice plane. Okay, so here first we need to find the intercepts of this plane on the coordinate axis. The intercepts are 1a, 1b, 1c, right? The coordinates will be 1, 1, 1. Reciprocals are 1, 1, 1, and hence the Miller index of this particular plane AGC is 1, 1, 1 in curved brackets. Now let us find the Miller index for this plane. Okay, so here the intercepts of this plane are on the x-axis, it is at half a. On the y-axis, it is 1b, and on the z-axis, it is half c. Okay, so the intercepts are half a, 1b, half c. The coordinates are half, 1 half. The reciprocals will be 2, 1, 2, and hence the Miller indices will be 2, 1, 2 in curved brackets. So in all these examples that we took, while taking the reciprocals, we did not have any denominators. If in any case you get a denominator, you should find the LCM to find the smallest integer. If a Miller index is given, how do we find the lattice plane from it? Let us see that. The Miller indices are given as 1, 2, 3. Now taking the reciprocal, we get 1, 1 by 2, 1 by 3. Hence, intercepts will be 1a, half b, and 1 by 3c. Now let's plot those points here. So on the x-axis, I have 1a, that will be here. And on the y-axis, I have half b, that will be here. And on the z-axis, I have 1 by 3rd c. So this distance is divided into 3 equal parts, and 1 by 3rd c will be along this point. So we plot these 3 points, and it's here, and we join these 3 points. This gives the lattice plane representing 1, 2, 3 Miller index. Okay. Now these Miller indices represent a parallel set of planes in that crystal. So here, a plane parallel to any one of the coordinate axes, x or y or z, it will have an intercept of infinity, right? One of the coordinates will be infinity. Now, if the Miller indices of two planes have the same ratio, that is like 844 or 211 or 422, these planes will be parallel, but they will not be equidistant. Now the HKL plane cuts the coordinate axis into H, K and L equal parts. Now it is important to have a notation system like the Miller index for crystal planes because these planes influence the optical properties, the reactivity, the surface tension and the dislocations of that crystal material. Now, if a cubic crystal is given, how do you find the density of that crystal? Now, assume that you have a cubic crystal and its lattice constant A is known. The number of atoms in the unit cell small n is known. Its atomic weight Ma is known. And Na is the Avogadro's number. We can write the density of the cubic crystal ρ as Ma times n divided by Avogadro number into A cube. This equation is of importance. Also, another important term in crystals that we need to know is the DSpacing in different crystal systems. DSpacing is the interplanar spacing between any two adjacent parallel planes of Miller index HKL. So if I have any two nearby planes of the same Miller index HKL, the distance between those two planes is the DSpacing. It is represented as small d usually. And in different crystal systems, it can be calculated using different equations using the Miller index H, K and L. It is given here. So for a cubic crystal system, the relation between the DSpacing small d and Miller index HKL is 1 by d square is equal to h square plus k square plus L square by A square. Now in the tetragonal crystal system, here 1 by d square is equal to h square plus k square by A square plus L square by C square. And in the orthorhombic crystal system, the relation for 1 by d square is given as h square by A square plus k square by B square plus L square by C square. Now in the hexagonal crystal system, 1 by d square is equal to 4 by 3 h square plus hk plus k square by A square plus L square by C square. In the monoclinic system, we have 1 by d square is equal to 1 by sine square beta whole into h square by a square plus k square sine square beta by b square plus L square by C square minus 2HL cos beta by AC. That's all for today's session. Thank you.